All right, let's dive in. Today, we're talking about the language that literally builds our digital world. Everything from your phone to the massive data centers that run the internet. We're going to peel back the curtain on Verilog, the blueprint for silicon reality.
But seriously, stop and think about that for a second. We're not talking about sketching on paper here. We're talking about telling millions, sometimes billions, of microscopic switches exactly what to do. How on earth do you even begin to do that?
Well, the answer is you use a special kind of language called a hardware description language, or HDL. Today, we're going to get to know one of the biggest ones out there, Verilog. Now, here's the thing to remember. This is less like writing software for an app and way more like drawing a super detailed electronic schematic, but with words. It's a whole different way of thinking. So let's see how it works.
Okay, first things first. Let's see how Verilog handles the most fundamental building blocks of, well, everything digital, basic logic. And to make it interesting, we're going to take one simple task and tackle it in 3 totally different ways.
So our little challenge is to model a specific logical rule, a Boolean function. What's so cool about Verilog is that it doesn't force you down one path. It's flexible. It lets you describe the same idea from different points of view. Okay, so this first method is about as direct as it gets. We use this keyword assign, which basically creates a permanent connection, like soldering a wire. It says the output SOP out is always equal to whatever this formula spits out. You can even see it in the code. The ampersands are your AND gates, the vertical bars are your OR gates. It's pretty much just like writing a math equation. All right, method number 2. This one's a little different. Instead of an equation, it describes the behavior. It's like a set of if-then-else rules. It says, hey, if the inputs A, B, and C are 0, 0, 1, then make the output a 1. Otherwise, if they're 0, 1, 0, make the output a 1, and so on. You're basically just describing the logic based on its truth table. And this is where it gets really, really cool. This is where you can feel the hardware in hardware description language. Here, we're not talking about formulas or behaviors. We are literally instantiating individual logic gates. A NOT gate, AND gates, an OR gate, and then we're wiring them all together. This is as close as you can get to drawing a circuit diagram in code. 3 very different methods, all leading to the exact same result. So making circuits that can calculate things is one thing, but what about making circuits that can remember things? That, my friends, is where the magic really starts. Let's see how Verilog makes circuits that can hold on to information. This is the big leap. The logic gates we just saw, they're called combinational. They have 0 memory. Their output depends only on the inputs at this very instant. Sequential logic is different. It has memory. What it does next is influenced by what happened in the past. This is the absolute foundation of computer memory, right here. And this little guy is one of the most fundamental memory building blocks, the D flip-flop. Its job is super important, but also incredibly simple. Whatever value is on its input, D, it stores that value and puts it on the output, Q. But, and this is the critical part, it only does this when it's told to. And the magic spell that makes this all happen is right here. This line of code, always at post-edge clock. That's what creates sequential logic. It's telling the circuit, listen, don't just change whenever you feel like it. I only want you to update your memory at the precise instant the clock signal goes from low to high. This is the heartbeat that keeps literally everything in a digital system synchronized. Okay, so we've got logic that can think, and we've got memory that can remember. So what happens when we put them together? Let's build something a bit more complex, something you definitely recognize, a simple counter. And would you look at that, you can see all the pieces coming together. We have our always at post clock block, so we know it has memory, and inside it's just some simple logic. On every single tick of the clock, it checks if the reset is active. If it is, bam, back to 0. If not, it just takes its current value, Q, and adds 1. That's it. It's a memory cell that knows how to count. But hold on a minute. This is the big question, the one that keeps hardware engineers up at night. You've written this elegant code, this perfect blueprint. But before you go and spend a ton of money to manufacture it into real silicon, how can you be absolutely 100% sure it's correct?
The answer is verification. And the unsung hero of this whole process is a piece of code that's just as important as the design itself. It's called the test bench. So, a test bench is basically another Verilog module whose only job in life is to test your actual design. Think of it like a virtual lab you build on your computer.
It pokes, prods, and generally tries to break your design, which we call the design under test, or DUT, just to make sure it behaves exactly like you expect it to.
This slide shows the relationship perfectly. The test bench on the right essentially wraps around our counter design on the left. The test bench is in total control. It's the one that generates the clock signal, it's the one that hits the reset button, and all the while, it's watching the output to make sure that counter is actually counting correctly. And if we go all the way back to our very first logic example, the test bench's job is to be exhaustive. It will literally feed it every single possible combination of inputs, from 000 all the way to 111, to guarantee the output is correct in every single case. By doing that, you can have complete confidence the logic is perfect.
Now for something like our D flip-flop, the test bench has a more active role. First, it has to create that clock signal, that steady heartbeat. Then, over a period of time, it will apply different values to the input and watch to make sure the flip-flop correctly grabs those values right on the rising edge of the clock. So why is this so incredibly important? Well, think of it like this. Finding a bug in your simulation costs maybe a few hours of your time. Finding that same bug after the chip has been physically manufactured can cost millions of dollars and cause months of delays. Verification is the firewall that stops a simple blueprint mistake from becoming a very, very expensive disaster. And it really all comes down to this. You can have the most clever, most brilliant hardware design in the world, but if you can't prove it works under all conditions, it's basically worthless. A design is only as good as the tests that prove it's correct. So there you have it. We've gone all the way from a single line of logic to the idea of memory to a complete functional counter, and even built a second system just to verify the first one. That's the real power of a language like Verilog. It lets you turn an idea into a physical, working reality. We've just taken a quick peek behind the curtain at the language that shapes our modern world. The building blocks are all there, ready to be put together. So now that you've seen the blueprint, what will you design?